Hi guys, welcome back to the channel. In this video we are going to implement the full adder with the help of 2x1 MUX, 4x1 MUX, 8x1 MUX. So let's get started. So if you observe, this is the full adder, the block diagram and circuit diagram. I hope you know this. For the implementation of the full adder, we can have many methods. So mainly three methods we have for the implementation of full adders or any logic circuit with the help of multiplexers. So the two methods that we have already discussed in the previous video. So this is the first method. First method includes if n variables, we are going to have n select lines. Suppose if you have example like if you have three variables, you are going to have the three select lines, means you have to use the definitely 8x1 multiplexer. But in the second method, it is not like that. If you have n variables, we can implement the multiplexer with the help of n-1 select lines. So that is the main usage in the second method. So we have highlighted the second method in the previous video. If you observe, we have three variables, we can use the 4x1 multiplexer for the implementing of that any of the logic. So we can implement the same truth table with the help of the second method. So if you observe, we are going to have another box. So we are going to implement this truth table logic with the help of only the 4x1 multiplexer. So in the 4x1 multiplexer, we are going to have two select lines. So the two select lines are A and B because we have three variables. So out of three, we are going to send two variables there. And the third variable should be sent as input lines. So for that, we are going to compare F and C and we are going to write as inputs. So I hope you know this. If you don't know, please check out that video. I am giving the iCards and in the as well as the description box. Check it out. Or if you want to know more about how multiplexer is used as a universal logic, and if you want to also know how all the logic gates, all 7 logic gates, how it is implemented with the help of multiplexer, so you can also watch the same video because all the content are provided in that same video only. So both of the methods and as well as the multiplexer used as the 7 logic gates, so in the same video, please check out this video. Now let's discuss about the third method. So for the implementation of the full adder, in this video we are going to just follow the third method because third method is important. So third method is easy. So if you compare both three of the methods, it is important for every of the methods. So we have to learn all the three methods. So if you observe this third one, so we can perform how many select lines we want with the help of the third method. So if you see the first statement, that is according to the method one. So if you have three variables, we are going to have three select lines in the first method. So in the second method, if three variables, we are going to have the two select lines according to the second method. But in the third method, we can implement the three variables with the help of only one select line. So let's see that. So before seeing the directly truth table, we are going to understand the basic concept behind that. So for that, I am taking a random logic that f is our output. So we are generally growing from 0 to 1, means that is 0 to 7, 1, 1, 1. So the output expression contains the 0 to 3, 7. So first we are going to implement these three variables. As we are having three variables, we are going to implement with the help of three methods, but we are going to follow the third method for more understanding. So if you observe here, we are going to have one select line and two inputs. So directly I am sending one select line as A, directly I am sending A. So we have left with another two things, that is B and C. So we are going to send this B and C as inputs to the I0 and I1. So let's see how to send B and C to the inputs, B as inputs. So this is some random function. So ABC is variables, F is our output. So this is some random function that in the question they have given. But we know the already for the 2x1 multiplexer the truth table, that is if A is 0, output would be I0. Means the select line is 1, then output inputs will be selected as that is I1. Now let's start understanding how to implement that. So if you observe, there is no need of truth table because we are just going to use the minterms. So if you see in the function that we have minterms 0 to 3, 7. So we are going to fill the k-map. I hope you know the k-map basics. So after filling that, so it is not like normal k-map grouping. We have to make another groups according to the MUX truth table. So we have to keep this in mind, and we have to go by row, not at a time whole things. We are going to don't see like that. We are going to have according to, suppose if you see the multiplexer table, truth table, that A is 0, that will select I0. The selector line is A, that is 0, that is I0 will select it. Then if you observe the k-map, then A is equals to row, first you have to select A is equals to row. Then you need to observe the B bar and C bar, means the B and C variables, how it is changing, and you need to obtain in the first row only, that is for I0. for A is equals to 0, you are going to check for BC how it is changing. So for the I naught, if you observe that for the first one I made separate group, that is B bar C bar. For the next group of 2 in the same row, you are going to have B, because B is not changing that. So I naught is equals to B bar C bar plus B. The next thing we are going to follow up is to find that I1. So I1 means what? The next row. So in the truth table of multiplexer, if you observe A is equals to 1, that we are going to select the I1. So in the K-map also, you are going to have A is equals to 1. Then you can observe how BC is changing. So in one position only we have BC, that is that position. So if you observe that position, that is BC. So I1 would be definitely BC. So as we all know, the output expressions, that is B bar C bar plus B as I naught and I1 as BC. So we can simply implement like this. So this is the circuit diagram that I can say with the help of 2x1 multiplexer. So this is some random function. This is not full adder. So full adder we will see now, but this is some example that they might ask any kind of implementation. They might give any logic expression. They might ask to implement this logic with the help of the multiplexer, or 2x1 multiplexer, 4x1 multiplexer, how you implement, how many AND gates are required. So these kind of questions might be asked in our gate exams or very important exams. So now let's start decoding all the full adder circuits. So with the help of first method, we are going to see the full adder implementation. With the help of second method also, we are going to see the full adder implementation. With the third method also, we are going to see the full adder implementation. So if you start with the first method, the full adder implementation. So according to the first method, we are going to see that we are going to require 8x1 multiplexer. So because we have 3 variables. So 3 variables means 3 select lines. So 3 select lines means total 8x1 multiplexer we need. So that's only written there. And for n variables, we need to have n select lines. So this is the sum expression, and that is the carry output expression. So if you observe simply, so total we have 3 variables. So we have the three select lines also. Simply we are going to pass all the 3 variables directly over that. That is S2, S1, S0, that is as A, B, C. So in the inputs also you can observe directly. I am passing at a time that directly the sum of inputs. That is, you can see the sum is output in the truth table, but you are going to pass as inputs in the 8x1 multiplexer, because based on inputs or based on select lines, we are going to select one of that. So if you observe 0, 0, 0, if you are passing as ABC, you are going to select the first one 0. Like that, you are going to check all. So you can see that just I am passing directly all the sum output expression, the column itself directly I am passing. So for the carry, the same thing. You have to just pass all the carry column wise. That's it directly, and you have to take the select lines as ABC directly. The same thing. So this is the first method for the implementation of 8x1. So this is not efficient thing, because we are using the higher multiplexer. So why we need to use the higher multiplexer? We need just with the help of, or if you don't have 8x1 multiplexer, then what we can do? So if you have only 2x1 multiplexer, so that kind of situations can be arised. So that we are going to see all the 3 implementations, all the 3 methods that we are going to see. So I hope you understood with the help of the first one, that is first method. So implementation of full adder with the 8x1 multiplexer. So now we are going to implement the full adder with the help of the second method also. So in the second method, we are going to have the n-1 select lines. So basically n means what? Total number of variables. So n-1, 2. So we are going to have total 2 select lines in this. So 2 select lines means what? 4x1 multiplexer we are going to use for this. So this is the sum carry as usual. So that is the written over there. That is n variables. We are going to use n-1 select lines. So I hope you know this procedure. If you don't know, please check out that video as I preferred before only. So if you observe the second method, just I am going to come. We are just directly passing AB as the select line, as you can observe over there, and the third variable is left over. So that third variable can be compared with sum, and we have to pass the third variable C as inputs. So if you observe sum and the C, so if you have both are same, so the first one, or the I naught would be, or D naught would be C directly. So in the same format, I am going to fill all the columns that you can observe over there. So next box, you can see that 0, 1, 1, 0. So that is exactly sum is opposite of C. So that I am going to have the S is equals to C bar. So the next one also. So S is equals to C bar. So if you observe the last 2 rows, that is 0, 0, 1, 1. That is for we have to compare the C and sum. Again, I am saying you are passing A, B as the select lines, and C sum you have to compare. So you have to represent the output in terms of C as input lines. So that is the main thing that we are going to observe. So if last observe, that is the same. So you are going to have the S is equals to C. So represent all the things that in the lines as that. So you can also observe there the 4x1 multiplexer is implemented as full adder. In the same way, we are also going to find the carry for that full adder with the help of 4x1 multiplexer. So we already know the same procedure. So just compare the C and C out. If you observe the first one, there is no relation between C and carry out. So there is no relation and the C is changing from 0 to 0. So just the first, the D naught or the I naught, any variable for the first one would be definitely 0. So if you compare the similar thing that for the next two rows, that is C and C out would be same, that is 0 1 0 1. So next I1 would be C. So like that you have to compare all. If you have compare the last two rows, that is 0 1 1 1. So there is no relation between C and carry, but C out is changing 1 1 from 1 to 1. So we are going to have the input as 1 in that case for 4x1 multiplexer. So as we already discussed this full adder with the help of 4x1 multiplexers. So for the circuit diagram you can also observe there. So for that, with the sum need that C variable and for its complement also. So simply I took a variable line and I simply represented like this. So I hope you know this how to represent. And the second carry also you can observe over there. Just I connected both of them. So now it's time to discuss the third method. So for the third method, if you observe for the full adder implementation with the help of 2x1 multiplexer, so this third method we have discussed an example so that you can able to understand or relate very simply. So this here we have total 3 variables in the full adder truth table. So we can be solved with the help of only the 2x1 multiplexer with the one select line. So let's see how to implement that. So the first step that we are going to find with the help of the 2x1 multiplexer is that to find the sum expression or sum implementation. So if you observe, this is a truth table that I have changed. So as we already learned the procedure, so in this also we are going to follow the same procedure. So first we have I naught. So for the I naught, if you consider the first row wise, so that is, if you see the MUX also, 0 is correct, A is 0. So we are passing directly A is as select line. So for the I naught we are going to have the A row. So if you consider A row in the K map, so we have two ones. So two ones can be grouped like that. So first group is B bar C, second one is B C bar. So we can simply add both of them. So the output would be I naught as B bar C plus B C bar. That is simply B XOR C. In the same way, we are also going to find now I1. So for the I1, if you observe, we have 2 1 in the positions of 4 and 7. So we can group as so row wise we are going to group. So if you observe 4, that is B bar C bar, that is in the 7th position, that is BC. So you add both of them, that is I1 expression. So I have marked in the 2x1 multiplexer also, you can observe there. So that is the XOR gate, that is B XOR C. So with the help of the third method, we have obtained the sum expressions. So or sum we are implemented with the help of 2x1 multiplexer. So for the carry also, so I have changed the truth table. Let's see that with the help of 2x1 multiplexer in the third method. So we don't need the truth table also for this because we can simply represent with the help of the K map. So the min terms are 3 5 6 7. So simply represent in the K map. So for the, according to the row wise, so we are going to have this just A is equals to 0 for the first row. So for that we can get the output as I naught for the first one. So if you observe, we have 3, we can make that as a single group. We should not make the 7 because it is not normal, not normal K map. We are going to follow the rules for the implementation of 2x1 multiplexer. So for that we can make that is BC. So simply I naught is BC. So in the same fashion, if you observe for A is equals to 1, you can see 5 7 made as a group, 7 6 can be made as a group. So we have two groups. So for the first blue group, if you observe, that is B is changing, so C is not changing. So that is C plus, so we have second group. So for the second group we can observe that B is not changing. So B plus C is our output, that is I1. So we can simply represent the B XOR C as input lines over there, that is for sum, and B dot C, that is I naught, I1 for B plus C, that is for carry. We can simply represent all that, and we can change, or we can also change a circuit diagram also. Simply we can convert that equations as the output expressions or the circuit diagram also. So if you observe for the sum, that is XOR, so we are also getting from the XOR also, because just invert that we are going to have the XOR. So that is I1. So for the, if you observe the carry, so first one we have B dot C as I naught and B plus C as I1. So simply that is the thing that I can say. I hope you understood this video. Thanks for watching up to now.